Oh no, AI will replace us all. So, can AI replace us? Let me clarify what I mean by that. When I say us, I'm talking about programmers. I don't think the answer for other knowledge workers are inherently different, but that's what we'll focus on. Also, when I say can replace, I mean, can AI leave the programmer completely out of the picture? Can we have a workflow that is completely and utterly devoid of a human at least looking at the code before it is fed into the compiler? So, can AI replace us? My answer is no. Not now, not in the near future. I think the predictions about that being possible within half a year or even 2 years are totally and completely off. Of course, that's totally different than asking, will AI replace us? But I'll address that in a different video. So allow me to introduce myself. Hello, my name is Shachar Shemesh. I have been programming for almost 45 years now, over 30 of which professionally. I've started programming in BASIC and assembly on the Apple II. It wasn't this precise computer, but it was so similar it might well have been. I've then switched to the Amiga, this time this actual computer, and then to PC on MS-DOS, Windows 95 and onwards, and then Linux. And the question I want to address today are whether coding agents can replace me, someone who's spent a lifetime honing his coding skills. There is a separate question about whether AI can replace developers who are more junior, but again, I will address that one in a separate video. I've been programming using Gemini, both the 2.5 and the 3 models at work. I've also played around with Claude Code version 4.5. I've also talked and read about other people around my level of seniority have to say after their own experience. From all of those, it seems very clear to me that the answer is no. Coding agents can be amazing helper tools, but they are not in a position to turn requirements into product, nor are they anywhere near that position or even with a feasible trajectory to get there anytime soon. I even have reasons to believe that the correct answer is not ever, but that argument is more complex and we'll have to wait for a different video. And yes, I've seen the countless testimonies of people who appear to have done just that, eliminate the programmer from the process. To understand what I mean, let's talk about product bringup. There is an open secret about tech products. When tech companies start a new product, they don't know what the hell they're doing. They're working off a vision of what the product will do and how it'll be useful to people, but that vision is rooted on nothing more than fantasy. The number of times this vision bore any relationship to reality is as close to zero as to not matter. If you don't think that's right, let me remind you of an oft forgotten fact. The first iPhone didn't have the App Store. The first generation iPhone did not allow installing third-party applications. So the best way to make a product mature is by releasing something. Nothing clarifies product's potential like actual users. To counter this, smart companies' first release is an MVP or minimal viable product. A good MVP is a product that there exists some customer who will find it at least somewhat useful. This is important to start generating revenue, or in the case of startups, to prove to your investors that you can deliver. But mostly, this is the best way to start getting real-world knowledge of how this abstract idea translates to the real world, what actual user pain points it's meant to solve, and what pain points it creates. Which means that software creation, or at least good software creation, is an iterative process. You start out with a concept, and then you have to pivot multiple times as the picture of what your actual product changes due to market exposure or the passage of time. Except something happens when that's the way you work. When you build a product, the top layer, the part that actually implements the product, is just a small part of the whole thing. A lot of the product is invisible to the user, built to support the ability to implement the interactions between the product's components. We call the part that directly affects the user business logic, and that other part infrastructure. And at this point, I need to make a distinction. I am what's called a system programmer. I generally write code in compiled language, built to interact directly with the operating system and sometimes the hardware itself. Products in this domain generally use a fairly thin layer of off the shelf infrastructure. System level products are usually a long term investment and usually carry a lot of their own infrastructure, built specifically for that product. The same is not typically true for the rapid development environments. There, the focus is on moving fast and getting products out quickly. As such, products aimed at web and cloud deployment typically use ready made infrastructure. A good web developer will know hundreds of libraries she can easily pull into the project to use, as well as hundreds, if not more, cloud services she can utilize. I call this wide knowledge as opposed to the deep knowledge a good systems programmer need. For the moment, I'm focusing on the systems programming case. I don't think things are fundamentally all that different, but my perspective on that other front is that of an outsider, so I'd rather not assume. Here's the thing. When you build a project, not every line of code you write is 100% optimal for what you want to do. Reasons can vary. Maybe where you were initially aiming turned out to be different than where you ended up going. Maybe doing things the right way takes more time and effort than you could afford to invest. Maybe you just make mistakes. Either way, with time, more and more of the code you're running diverges from the code you'd ideally be using had time and resources been unlimited. The difference is called technical debt. As your technical debt increases, making changes to your code base becomes more and more difficult. Parts of the infrastructure are simply working against you doing what you want to do instead of helping you out. I call that the interest you pay over your technical debt. And just like compound interest, as you have to jump through more and more hoops to make your tasks fit the infrastructure you have, you write more and more bad code that increases your technical debt further. Here's the problem. Design written by current AI models, and I've already listed what I've used, have a lot of technical debt baked in from the start. If you do what everyone says you should do, describe what you want the result to be like, and let the agent go to town, the resulting code is a mess. Germany produces code that actually works, going as far as writing the test cases for me and making sure they run and pass, but the code quality and design decisions are horrible. Code gets repeated all over the place, inefficient data structure and API usage is common, and the entire thing just feels uninspired. For Claude, I did not give it as fair a test. I asked it to do something over a hardware project, and since this is a hardware project, I did not give it a chance to run and see how things go and fix it. I did look at its first suggestion. At first, it made a fairly basic mistake about what the requirements even were. When I fixed that, it produced code that didn't work, but was close enough for me to assume that, given the ability to run and correct its own mistakes, it would have gotten there. But while I fully believe the code would have worked, it was not good code by any stretch. Hardware projects are essentially state machines. Claude's implementation just edits states to make things work. It did not pick up existing states that could have been merged, or nor did it pick up the preparations they made that could be utilized. In other words, it too was uninspired. Coding agents are supposed to be a multiplier. Now, let me state right here and now, they absolutely are. With a good coding agent, and someone else picking up the tab, I'm slowly converging on a workflow that indeed increases my productivity. But while it is a multiplier, it is nowhere near a times 10 multiplier. Even times 2 is at this point a stretch. The reason is that even if I found a workflow where it produces reasonably good code very quickly, that is not the development cycle's bottleneck. The bottleneck is me. No matter how quickly it produces the code, I still have to read and understand it. And understanding code written by someone else, even when it's written to your specs, is a time consuming effort. Now, in my day job, I already read code written by other people. After all, that's what code reviews are. But this is not the same type of reading. More on that in a bit. Of course, AI proponents have an easy rebuttal. Don't read the code. According to them, I should give a prompt, get working code, and that's it. Since I've already said current generation agents are clearly capable of doing that, and as I've already said that that's what prevented me from using AI to reach 10 times speedups, this seems rather obvious. Now, if you think about it, we already have a tool that converts our intent into something the compiler can run. It's called a compiler. It takes C++ code, for example, and converts it to assembly. And while I do on some rare occasions open up the resulting assembly to check it, these occasions are very rare indeed, and I'm also betting I'm the exception on that front. Most people trust their compilers to produce code that correctly and accurately represents what their C++ or Rust or C or whatever source code said. Which is why I call this approach C++ as assembly. We treat the AI agent like a compiler, our prompt like the source, and the resulting code like we treat assembly, to be read only on rare occasions. If I understand it correctly, here's the reasoning given. Yes, the code produced by AI agents is uninspired, but it doesn't need to be inspired. It needs to work. As for technical debt, what does it matter if making changes becomes more difficult if the agent can still complete them much quicker than you could have? There are multiple reasons why I think this approach is not smart, bordering on downright dangerous. The first is that prompts are not source code, and the resulting code is not assembly. The particular aspect I'm referring to here is this. When I compile a C++ program, the C++ source code is all that's required to generate my program. If you take my source code and compile it yourself with the same compiler, you'll get the same assembly program. The process is extremely repeatable. Conversely, if you compile my source code with a different compiler or for a different platform, you might get a different assembly, but that different assembly will still do the same things as my compiled program. The translation of source code to assembly is very well defined. This means that we normally assume that to understand the program, its logic and its bugs, we don't need to examine the assembly. The source code will tell us everything we need to know about it. That's precisely the reason we don't normally examine the assembly. But AI agent prompts are not like that. First of all, they're not shipped. Many don't even store them for later examination. We can audit a program by auditing a C++ source code. We cannot audit a program by auditing the prompt that created it. Now, that last part isn't globally true. Some people store not only their entire agent conversations into the source repo, but also the AI's logic and reasoning. Even then, those don't function as source code. I cannot regenerate your program by feeding the same prompts to my AI agent. That's definitely true if we're using different AI agents or different versions, but it's true even if we're using the same agent and version. Even using your prompts, I'll get a different program that works more or less subtly differently. The prompts simply do not fully define the resulting program. Nowhere is this more obvious than when it's time to make changes in the program. When we want to change a compiled program, we make changes to the source code and rerun the compilation process. This means that just like the original translation of source code to assembly is well defined, so too are the changes we introduced. More importantly, the difference between the program before and after the change is well defined. But when we want to change the code using AI, we do not describe the new program post change. We describe the change itself. What the agent then does greatly depends on how we got to that point. If the change is requested in the same session as the original prompt that created the program, the agent will consider the original prompt as part of its considerations of what the post change code will look like. But we can request changes to the program in a different session as well. When we do that, the agent does not, in fact, look at our original prompt at all. Instead, it looks at our produced code, tries to deduce what the program was supposed to do, and from that, deduce what the new changes need to be. In other words, we cannot treat the resulting code as assembly because the AI agents sure don't. Which brings up an important point, which is this. How does the AI parse our source code? An AI agent keeps track of your conversation, which includes both the prompts you give it and the data it has to parse to work with it, using points in a multidimensional graph. These are called tokens. The number of tokens a large language model can track is called the context window. When a context window is full, one way or another, it has to forget something before it can learn anything new. Now, current generation AI agents have a context window that is quite large. Claude Code, for example, has a context window of 1 million tokens. Surely that ought to be enough, right? I mean, I don't know about you, but I sure can't remember 1 million pieces of information about any program I'm working on. And the answer is that it is enough if, and that's the important part, the code it has to parse is well written for some definition of the term. And what, you might be asking, constitute well written code? So glad you asked. Well written code is code where you can deduce its functionality without reading, parsing, and remembering all of it, which is a kind of recursive definition, but bear with me for a minute. Because as I've said, Claude's ability to remember things about my code is greater than my own. So how do humans deal with the need to make changes in code? The answer is that well written, for the sake of AI agents, is the same well written as for humans. In other words, code that is easy for humans to maintain is code that is easy for AI agents to maintain, and vice versa. All of the things that make code good for humans, such as abstractions, encapsulations, preventing repetitions, and so on, are designed precisely with that purpose in mind, reducing the amount of context a human needs to keep in their head in order to safely make changes. Which means that when we create code with technical debt, code that is harder to maintain, it's not just humans that have to work harder to maintain it. It's also the AI agents that have to work harder. So here's the danger. You start working with an AI agent. You vibe code to your heart's content, and everything is great. The code works, and all's good. You don't look at the resulting code because that's like checking the compiler's assembly. It might be terrible, but who cares? You don't have to maintain it. The AI does. But then the product succeeds, and the code base grows. It soon grows beyond the scope of what a human can deal with, but so what? A human doesn't have to deal with it. The AI has 1 million tokens context window. But then the code grows beyond what the AI can deal with. Now, there are two things people need to, and most probably don't, realize about this point. The first is just how sharply the agent's ability to make changes that make any sort of sense drop. This is not a gradual decline in change quality. While this will also not be a total cliff effect, it's closer to the latter than to the former. The second thing people don't realize about this point is that under many agents, it will not be obvious. Some agents let you know when the context window fills up and stop processing. When that happens, you at least don't get nonsense changes to your code. But consider what you will get. You load the agent, write a single prompt, and the agent will tell you it ran out of context window to carry it out. A literal cliff. But that's the best case scenario. Many agents don't know when they don't know. They continue to give confident sounding answers even when they are completely hallucinating those answers. For those agents, if or when your codebase becomes too complicated to fit inside the context window, the AI will hallucinate code changes. And let there be no mistake, those code changes will compile. They will pass tests who themselves may be checking hallucinated criteria. Things will appear to continue to function for quite a while past the point where they actually don't. Because that's the point about AI generated content. It's optimized to look good, even when it's meaningless. And here's where things become dicey. While it's convenient to think of the context window's memory with which the LLM works, that's not actually how this operates. Memory can be increased with very little effort. Just buy some more and you're done. I mean, it's insanely expensive right now, and AI is the cited reason, but still, it's just a matter of money and time, which, as we all know, is also money. But the context window isn't just the memory in which it is stored. The context window is fed to the neural network that drives the agent, and so the network has to be trained with a certain context window size in mind. Changing the context size means retraining the network, and that in turn has quite far-reaching implications. I've tried to keep the discussion neutral of current capabilities, focusing on generic and hopefully time-insensitive aspects. With a field that moves so quickly, it's obviously hard to tell for sure. So far, I've covered the technical aspects of AI agents as programmers, but aside from those, there are multiple other factors to consider. The two most important to me are the economical and the business factors. This video, however, has been long enough, so I'll talk about those next time. Subscribing will improve your chances of hearing about that next time video, though. Thank you for watching.